slide is going to be the fastest of all. So this talk is about running languages on top of Microsoft's .NET framework of common language infrastructure. This is one runtime engine designed to run lots of different languages. The runtime engine has a single bytecode format that I'm going to show you how we translate Python into. It has a just-in-time compiler, has a garbage collector, it has reflection and load time support, all the sorts of things you need to implement a language like Python. Lots of languages are in production use today running on top of this platform. I should actually add Python to this list now, because I know as of about a month ago there are, even though we still call it a beta, there's Python in production use on top of this platform. Always makes me nervous when people do that with a beta, but it's a great way for us to get feedback, so thanks. And it's an international standard. It's an ECMA and ISO standard, just common language infrastructure, and there's several open source implementations available. Mono, which is Miguel Diacaz's project, is far and away the most mature of all of those open source implementations. I always have to show this slide because I really enjoy the fact that you can go to the Microsoft download page, their main website, find under the Visual Studio logo a copy of Python to download. That's a lot of fun. So this is the place that you go to get a copy of IronPython if you want to get the latest bits. And this zip file comes with source code for the whole engine. And we're actually a little upset that it's 900K. We'd like to cut it down to about 500. Python regression test suite. Anybody who was at Martin's talk has seen this before. Those of you who missed it, this is how much of the Python regression test suite we ran last year at PyCon. There you go. We've done a little bit of work since then. Fortunately, this year I don't have to give the same talk that I did last time about the missing 6-month gap that I couldn't account for. This, I think, accounts for the last year fairly well. So this is the part of the Python regression test suite that we run, a large fraction of it without changes. And it includes a lot of the sort of major modules like grammar and built-in and binary operators and all those sorts of core parts of the language. The things that we aren't running, obviously, are things that have to do with a lot of C-based extension modules that we don't support yet. Give you an example of when we say we're running things with changes. This is an example of a change that I have no qualms about whatsoever. I don't know who can read this. I think Raymond wrote this test, actually, but we'll find out. This is for the enumerate, new enumerate built-in function. And this test, well, I'll explain it, because I think the person who wrote it might be the one who can figure it out from the code. Tests that when you enumerate, it reuses the tuple, so that you're only using a single object, that this map is only creating a single object, and it's using ID to check that you're reusing the tuple every time around when it's possible. So this is one of those tests that's, it's testing an implementation optimization, which is great to have around, but really doesn't have anything to do about being an implementation of the Python language. It also requires reference counting to even get right. So this kind of test, we're never going to pass, and I don't think there's any problem with that. We also have some interesting open questions that we need to start a dialogue with folks about. This one is a test that's testing that getAttr can't accept Unicode strings. And it's a test saying that you can't pass a Unicode string into the getAttr for a function because Python attributes all have to be ASCII strings. On the .NET world, a lot of programmers really want to use Unicode identifiers as their attributes. So right now, we allow you to pass Unicode strings to getAttr. Whether or not that's within the realm, that's one of those questions that feels on the border as to whether or not it fits within being Python or breaking Python by deciding to allow Unicode strings. These are the kinds of things that we're finding by running the regression test suite. Okay, now moving into implementation. This is the IronPython architecture, which I've shown before, and I will spend very little time on because it's the same as the CPython architecture. Actually, it's now the same as the CPython architecture, now that CPython's moved to having an abstract syntax tree. I've always said this was the same as the CPython architecture. I'm thrilled the new changes that have happened to the compiler have made this true. So thank you, Jeremy, and everybody else who was involved in getting the ASD stuff in. So it's a totally normal compiler, tokenizer, generates an abstract syntax tree. The difference is, of course, it generates IL, which is this common bytecode format, rather than Python IL. And it also has a support library that's not built in C, it's built in C#. It's built on top of the languages of the .NET framework. So I'm going to have 2 slides that I've shown before. So those of you who have seen them, tune out for just 1 minute, but come back quickly. This is how we compile factorial function to IL. And here I'm just showing the compilation of this if test. So this one line gets compiled to these Python opcodes. This came out of the DIS module. And to this IL by IronPython, this common language, intermediate language that runs on top of .NET. And you find for some of the opcodes, there's this amazing match, right? Python has a load fast 0, which is using for loading local variables in a function. .NET has a load arg0 that has exactly the same behavior. So those translate perfectly. Loading constants translate fairly well. .NET's constants are slightly different than Python's, so we load those out of static fields. We populate a bunch of static fields with all of the constant to fill up the constant pool, and then we load those out of static fields. And then there are the fun things like equals. .NET has an equals opcode, but it has no dynamic properties. It doesn't go out and look for an under EQ method, then look for an under CMP method. I'm sure there's an under coerce in there somewhere if I could actually remember how it all ties together. And follow the full dynamic rules that Python has for doing equality comparison. So when we have these complicated opcodes, we turn them into static methods. And I'll talk a little bit about those static methods in a moment more. So the opcodes either match extremely closely, as in the load fast, sort of closely with the constant pool, or we fall back to static methods. Now, if you look at this, the Python bytecodes reflect the Python source code. They're simpler than the IL ones. There's a little bit less code over here. They're doing simpler things. You'd think that they would run faster. So the question is, why does the IL run faster? And this is the reason why. The IL gets translated down to machine code at the end of the day by the just-in-time compiler. Some of the opcodes become 100 times faster. The one that truly becomes 100 times faster is this load fast 0. Because it goes from having to go around the Python opcode evaluation loop a full time, which is about 100 instructions, give or take. Somebody here might know that number better than me, but let's call it 100 instructions to go around the loop, to a single move instruction from one register to another. So that's the case where we get the huge improvements. Things like the constant loading is also noticeably faster because it's, again, turned into a single instruction. It's a move from memory, which has its own overhead. And then things like compare run at roughly the same speed in IronPython as they do in CPython today. So the game with IronPython is finding the things that we can optimize massively and getting these sort of 10x or 100x improvements, and the other stuff making sure that it runs as fast as CPython. So at the end of the day, you wind up with noticeable performance improvements across the board. Unfortunately, we can't get the 100x everywhere, or I'd have a whole different talk to give today. I'd love to give that one someday. Maybe next year. So I want to show you, anybody who's interested in playing with IronPython, I'm going to give a quick demo of looking at the code that IronPython creates and the way that we do it and some of the tools that are available on .NET. This is a little bat file that I have for running IronPython with some flags set. And the important flags are I'm running it in debug mode and asking it to save assemblies. You can find all of the flags. None of this is mysterious. You just pass the question mark option. It gives you all of the options and tells you about those flags. So if I run with those flags on, I'll generate .NET assemblies to disk that I can now look at with all of the tools that are available for them. So here's the factorial program, same one I showed you before. And I'm running it in IronPython, and I get an exe at the end of the day. And here's the exe popping up. This is the .NET assembly that comes. It has, as its top level, a class called under main. Because as you all know, if you pass a module to Python at the top level, you get a under main module created. So this is the equivalent of that. It's got a bunch of things in here that, well, it's got an under doc, an under name. So these things all sit on every module. These two are the two constant pool entries. This is for the integer 1 and the integer 10. This factorial is the pointer to the factorial function through a level of indirection, because you need levels of indirection in Python, because factorial is just a variable. We won't talk about this one. Let's look at the constructor for just a moment. So the constructor, all that it's doing, the class constructor, is building up the constant pool. So it's going through here, it's loading the constant 1, turning it into a boxed integer, which means it's turning it from a literal constant into an object. And everything in Python needs to be an object. And then it's storing it into the constant pool. And then it's loading 10, boxing it, storing it into the constant pool. So that's the sort of thing that goes on in initializing the constant pool. The module itself always starts with this initialize method. This is the top level code for the module. And what this code does is first it sets the doc string. There doesn't happen to be one in this case, so it's setting it to none. Then it's creating the factorial function. And there's a whole bunch of code here for creating the factorial function. There's a bunch of information that we want to put into the function. The interesting part of it is this part here that's loading a pointer to this other static function that's saying this is where the actual code for the factorial function lives. Then go down to the bottom and show the part that you can, I think, explain more easily. This is getting ready to call the factorial function. So it loads an object, it calls it, and then it calls print to print the result. So that's the call to the factorial function. Let's look at the code to it briefly and then move on. So here's all the code to the factorial function, which I showed you earlier. Here's the load arg0, the load static field, the call, etc. going on through. There's a few no-ops in place. These all get thrown away by the JIT compiler. The no-ops are there. Actually, Jeremy talked about this too. Keeping track of line numbers is one of the most challenging things to do effectively in the compiler backend, and yet it's incredibly vital for a language like Python, because errors happen at runtime often instead of at compile time. So you need to keep track of line numbers very carefully. So the bytecode that IronPython generates will often have some extra no-ops thrown in to make it a little bit easier to keep track of our line numbers. That's how we do it, rather than having a complicated line number table to keep track of. Okay, so that's inspecting the code. I just added these two slides after seeing the previous talk, so I thought I should show you what the code gen looks like. This is the code for the AST that we have for a return statement. So a return statement here, this is C# code. Shouldn't be very surprising to anybody who's read Java code, or C code for that matter. This is the code for the return node in the AST. So the return statement has a single expression as a field. So it has the expression that you want to return. And every statement has an emit method that can be overridden. We don't get to, we're denied the joy of dealing with unions, structured tag unions here. So we have to use classes instead and overriding methods rather than the joy of the C implementation. And here it's just we emit the position of the return statement, because we want to keep track of that, and then we emit a return that generates the expression. I realize this has got a little bit too much hidden behind the scenes here. Sorry about that. Let me go to while, where there's nothing hidden behind the scenes, which is why it takes up the whole slide. While has a test, which is the while test that you want to do, the test expression. It has a body and an optional else. And the else has this underscore after it, because else is a keyword in C#, just like it is in Python, so we can't use the else directly. And the emit code here, we define labels for the 3 different places where we might need to jump in a while. There's an end of the while loop, there's a place that break goes to, and where continue goes to. And end and break usually go to the same place in most programming languages, but because Python has this else clause, end and break have different targets. Then we go through and walk. We set the continue target to be the top of the loop, because that's where continue goes back to. We emit the code for the test expression. This is one of those calls, recursive calls down. We ask the test expression to generate itself as a test. And then we branch if it's false to the end of the while loop. Otherwise, we go through and do the loop. Here we set the break target and continue target. We emit the body. We tell it to break to continue. So it continually loops around back to continue if nobody does anything explicitly. We mark the end of the while loop, and then we generate the else clause. So that's what the code generation looks like coming from C#. Object layout. This was interesting. I was really hoping that I was going to show that we have a more compact object layout than CPython doesn't. Because if you think about it naively, we should. .NET uses a true garbage collector, so it doesn't need to have a ref count. So if you look at the layout of an integer in CPython, it has these 3 pointer-sized blocks. It has a reference count, which is an integer keeping track of how many references there are to the object. It has a pointer to the type of the object, and it has the actual int value. Well, on .NET, it's obvious that we still need the type pointer, because again, it has runtime typing, so you need to be able to find out the type of any object at runtime. So we have the type pointer, and we have the int value. But we also have this fun structure that replaces the reference count called the sync block. And this is where a whole bunch of extra information is stored in flags. The kinds of things that the sync block stores it can be used for doing very lightweight locking. By not having to add anything, you can use some flags in here to do locking. The garbage collector uses this to mark objects. Sometimes when it's preparing them for finalization, it'll use some flags in it. A number of the bits are reserved for if you ask for the hash code of an object that hasn't overridden hash code. It'll stick another random integer in this place so it can always give you the same hash code for a given object. So this extra sync block is used to be able to store arbitrary information. Well, 32 bits worth of arbitrary information in every object. So it turns out that integers are exactly the same size in CPython and in IronPython. My conclusion from that is there aren't actually that many ways to do this. If you want to represent an integer and you want it to be a dynamic type object that's holding onto its type, this is kind of the structure you're going to wind up with at the end of the day. IronPython's ints, though, it's interesting. These are just the plain ordinary boxed ints that everybody else on top of .NET uses to represent an int as an object. So we're not using special Python objects here, and yet they turn out to be exactly the same as Python's objects. Lists also turn out to be virtually identical, somewhat surprisingly. So lists, again, there's the ref count sync block, type pointers, a count of the number of actual items that are sitting in the list, and a pointer to an array that contains the actual data. There's one thing I'm not saying here, which is it turns out there's one more word in the .NET implementation, because the array that .NET uses has an integer to keep track of the number of objects in it to prevent people from having buffer overflows. So we get one more. Yes, Jeremy?
You also skipped one type is the double linked list is for the garbage collector.
The doubly linked list in Python used for the garbage collector? Yeah, we don't have to do that one.
Right, so I don't see that on here.
Oh, list has one of those?
Yeah.
Oh, great.
Probably is too.
Okay, let's add. So what about the type pointer? So it's, I'm saying these objects are exactly identical because they both have this type pointer, but the type pointer is going to look a little bit different in IronPython than it does in CPython. And here I get to give my very brief, there are two ways to implement Python running on top of a static virtual machine. And I've done both of them, so if somebody comes up with a third, let me know. But I believe these are the only two sensible ways to do it. One is you make all of your objects a subtype of some magic py object type. And then every time you have something on the stack, you know what type it is, and it can have operations on it like under add or under get item that correspond to the kinds of things that we expect to have on Python type objects. That's the approach that Jython takes. It's a very natural approach for doing this. It requires wrapping. All standard Java objects, anything that isn't a subtype of py object, when it comes into the system needs to be wrapped in a py object, and then unwrapped when it goes back out. And you have a lot of wrapping and unwrapping going on if you want to interoperate with other languages. So for IronPython, we tried to minimize that because one of our main goals is interoperation with all the rest of the .NET framework. So we leave everything a standard object. We still have to do some wrapping because Python objects behave somewhat differently than .NET ones. So we wrap the .NET types instead of wrapping the objects. And there's a lot less types in the world than there are objects. There's one type per large family of objects, so we do a lot less wrapping than we would need to otherwise. Let me be a little bit more concrete about that. This is roughly what the py object model would look like for implementing a string. This is more or less Jython's code. At least it was more or less Jython's code 7 years ago. So here's a Python string that's a subtype. This colon, I'm not using Java syntax here. I'm using C# syntax everywhere just to have one syntax. This says that py string is a subtype of py object. And it has a string. A Java string is its internal value. So it's holding on to a Java string as the actual value. It's just wrapping it. It has methods on it like strip that we have in Python. And here it returns, it takes its underlying value, calls the Java method, C# method in this case, trim, that's the equivalent of strip, and then rewraps it again. So you see the wrapping and unwrapping going on here. Just in calling this strip method, we're having to pull out the value from the inside of ourselves, do the operation on it, wrap it up again in a string, and pass it back to the world. Things like the add method, this can be implemented as a virtual method that you expect every py object to have. And the add method here, and I'm sure I'm missing some edge cases, but it basically checks to see if you're trying to add it to a string. If you are, it goes ahead and adds the value. It pulls the value out of the other guy. Oh, already found a bug. Okay, and please don't complain about my formatting. Pulls things out, adds them together, pushes them back into this wrapper. And otherwise, it could return not implemented with the new way that add works in Python these days. This used to be a lot more complicated. So the pure object model, you still need to have these string operations somewhere, but you can implement them as static methods rather than as methods on a py string that work on the actual .NET string objects. So here we have a static class of string operations. And it has in it this same strip method, but it takes in a string, and we call the parameters self for what I hope are obvious reasons to everybody in this room. They aren't obvious reasons to anybody anywhere else, but this is the string object that the method is effectively on. And here it just returns, in this case, the .NET trim method called on the string, because strip happens to correspond directly to another .NET method. So we're able to call it, to implement the method here as a static method rather than having to override the class. How we do dispatch, I will get to at the very end if there's time. And the add method as well, we take a self argument as string, we take in an object as other. If it's a string, we just add them together, and there isn't the wrapping and unwrapping going on. So I wanted to get to what happens when you do a subtype. And I happen to do subtype of list because I'd already drawn list for you once. Assume that there's 3 more big blocks sitting over here on the pink side, on the Python side, that I need to add for keeping track of the garbage collector. That makes up, because I've now added yet 1 more block on the IronPython side, so the more that we can put over on the Python side, the better. So here's the CPython. In the ref count, the type pointer count, the data. We've got the same thing over here, but when you subtype it, so in CPython, if you subtype a built-in and you don't specify slots, you can ignore it, and you want to have an arbitrary dict, so you can have arbitrary objects added, plus you have a slot, you're going to get this data structure where you take up one entry for the under dict, and 1 entry for the specific slot that you've added. It would be unusual to add both a specific slot and an under dict, but it makes the slides easier.
And weakref.
Yeah, well, I'm piling those up on top. Those are the, yes. Over here, on the IronPython side, we have the same thing, the under dict. We have the slot for my field, but we also have up here this under class. And the reason is that the under class is different from the CLR type. And let me try and explain a little bit about why that's true. The main reason for that is it allows changing the type of an instance. This was one of my great revelations. About 2 years ago, I started working on the Parrot Bench benchmark. 2 years ago? Yes, it was. And going through it, and everything was going well, and I had my object model all figured out, and I didn't have this extra under class, and I hit this code that changes this super type of an object that's subclassing from a built-in type, and my mind says that shouldn't be possible, and I think about it further and realize, okay, actually that's pretty darn Pythonic, so I better figure out how to support it. So what this under class does is it lets you change the type of an object as exposed to Python. You can't change the type of an object as exposed to .NET, because that's a hard and fast. In the .NET framework, you can't change the type of an existing object. I think that's actually a very good choice that they've made. By having that assumption in the .NET framework, there's a whole bunch of optimizations that can be done to the code. And it turns out the vast majority of code in the world never needs to do that. So enabling those optimizations is a wonderful trade-off. What we do in IronPython is say, well, on the other hand, there is this set of very dynamic code that we want to have this ability to change the classes arbitrarily of. So for this code, we're going to have an extra pointer. We're going to give up a little bit of performance in the code that we want to be more dynamic in order to have that dynamic experience. And there's similar rules to changing new style instance types. I can't take a Python instance that's of a subtype of list and turn it into something that's a subtype of dictionary, because the underlying object layouts are different between those two. IronPython has the same sort of restrictions. in what you can change. And I'll show you that changing in just a moment. And then the under dict slot is how you're allowed to add arbitrary attributes to Python objects. That can just hold a dictionary, just like it does in CPython. And we make sure that every time that we go through and do attribute access, we go through that dictionary. Implementing all the CLR features was actually really a pleasure, particularly in light of Python 2.2. Is it Python 2.2 or new style?
Yep.
Yes. Fields, and so Jython had gone through and sort of cobbled together a way of doing this that looked a lot like Python 2.2, but it was done before it, and the model wasn't particularly clear, I'd say, because it was sort of trying to figure it out on the fly. With IronPython, I had the benefit of, well, knowing what happened with Jython and seeing Python 2.2, so it gave me, descriptors was a very nice model to think about how all of this interaction worked. So fields for CLR objects work just like descriptors for slots inside of CPython. Delete happens, is forbidden on them because you can't actually uninitialize a field, but they work just like descriptors. They're a descriptor sitting in the class dictionary for the CLR object. Properties, again, are descriptors, just like @property. Methods, there's a little bit here. You can have overloaded methods on .NET. You can have methods where you have two methods with the same name and same number of arguments, one that takes a string and one that takes an integer. And those are just implemented by merging those two into one method that says, well, was I called with a string? Call the string one. Was I called with an int? Call the int one. It does that. And that turns them into a single method. And then it's just like methods for built-in types in Python. Constructors get turned into under new. This was another nice step forward. Constructors in Java never match the under init behavior, but they match very nicely onto the under new behavior that we have in CPython. So having under new, they match relatively nicely. Events, again, are done with descriptors. Events in .NET allow you to bind callable objects to, for example, a button click. You can say, whenever I click a button, do this. We'll demo that in just a moment if you don't know what the events are. And that uses a descriptor that returns a bound event object, just like a bound method, and it overrides under IAdd and under ISub to let you bind callables to it. So my general lesson for implementing CLR features was descriptors do the right thing. Hooray for new style classes. It made it really easy to have built-in types and .NET types be treated virtually the same. So there was a great coming together there of how those different ideas worked. So I'm going to load in. I can't do a demo here without showing one of the .NET libraries that I like, so I'm going to load the Windows Presentation Framework, previously known as Avalon, really quickly. So I can load that in. I can create a window. I can pop it up on the screen. Here's that window. Make it a little smaller. I can create a button. I can set properties on the button. This is the content. I can add the button to the window. And there we go. Isn't that impressive? I have to make the font size a little bigger. Okay. But now, so I've shown that before. Again, getting to how some of the internals work. For events, instead of just binding a method, I'm going to bind a callable class instance. That look right to everybody? I hope so. So I can now bind an instance of call me to this .NET event. And it'll work just fine. And now I should be able to click it, and it's calling the instance. It's telling me the instance that it was called on and the parameters that were passed to it. So all of this binding going back and forth between .NET, it's using the dynamic features of Python. It's not that we can just do functions, but as you'd expect in Python, you can do anything that's a callable object. Let's create now a subtype of a .NET class. We can create myPanel, which extends panel. This is one of those GUI classes. It's going to override the onRender method. Because what do I do when I render this? And we're going to be really exciting for this first version. Now I can create an instance of my panel and stick it in the window. Now I have this great thing. You see it was rendered once. Now, .NET has a retained mode rendering structure, so things only get rendered when you change things like their size. But every time I change the size, it's recalling the render. So I was able to override the onRender method while subtyping from it in Python just fine. Now, some of the fun part is let's import a bunch of panels here. And here's all the panels sitting there. They're really exciting because I coded them up on the airplane. We'll just show you what they do, but I can take this panel and set its under class. Panels.new panel. And now I've changed the class of it, and now if I move it, the renderer updates because it's now getting the onRender that comes from this new class. And I have. I can mess around with that. I can set it back to my panel. Of course, I can also define my render of P drawing context, and have it called panels.drawRect. This takes a drawing context, an object for the size, and let's give it a color. What's your favorite color?
Green.
We'll go with green. Huh?
Typical Microsoft attitude to the customer requirement.
Green came in the front row. I'm more responsive to the customers who can come up and hit me in the head than the ones who are in the back row. So now I can change the onRender method sitting in the myPanel class to be this myRender method. And now I've just overridden the method without changing the class. So it's calling the myRender method. So all of the sorts of dynamic things that you expect from Python code work just fine with .NET classes that are sitting inside of a .NET framework that expects everything to work. Okay, that's the end of the demo. So let's finish up with two of what I thought were the most interesting hard design decisions. First of all, I got a seemingly simple question for this crowd. I have this Python code. It says s equals, quote, some spaces, py. I call s.strip, I get py. Right? Obviously. I call s.capital_trim. What happens?
Name error.
I was, name error, close.
Attribute error.
So Python developer says should throw attribute error. That's exactly what it should do. There is no trim method defined on string. You're not Python compatible if you don't throw attribute error. Well, if I ask this question in a different crowd, I was hoping for a more overwhelming response from this crowd, but if I ask this to a crowd of .NET developers, they'll say that should call the .NET trim method. Strings have a method called trim on it. They say it needs to do this to be compatible with their .NET programming experience. They know how to program on top of .NET. They don't want to have to learn to call lowercase strip. Some of the experience that people have with programming languages is familiarity with a framework. This is one of those horrible questions of, well, and let me go back. My opinion here is both people are completely right. 100% absolutely right. So we spent a lot of time thinking about this, and it was funny because I would talk with Python developers who would say, this is not a hard question. I don't know why you're spending time on it. It's obvious, you should just throw attribute error. And I would go back and talk with people on the CLR team who would say, this is not a hard question. I don't know why you're struggling with it. Just call the damn trim method. And I felt a little torn. So we spent a lot of time trying to come up with design decisions, and this one was suggested by, oddly enough, one person with a fairly good Python design sense. His name starts with a G. Which was fighting through how to deal with the changes that he wanted to make to division. So in CPython, in Python, IronPython as well, all Python implementations, today 1 divided by 0 generates a 0 division error, saying you attempted to divide by 0. Let's see, 1 divided by 2. There we go. And it should generate 0.5. Better. 1 divided by 2, it doesn't generate divide by 0, but it returns 0. Sorry that I had the slide wrong. But if you do from under future import division, it returns 0.5. And what happens here is this special import changes on a per module basis the behavior of the division operator in Python to move towards ones that people who want this kind of true division can have this import and change on a per module basis. It's very important that it's per module. It means if I've written a module where I'm assuming the old division behavior and you import it into your code, it'll work just great. You don't need to know that I happen to want this future division and you want the old division. Each module gets to pick what kind of division that it has. So we're trying the same thing in IronPython, and so far it's gone well. Actually, so far only it's been the .NET folks who've yelled at me about this decision, but not nearly as loud as they were before, so it's a good sign. So here what happens, again, if you start up an IronPython console, you create the string, you call trim, you get an attribute error. It's exactly what you should get. If you import CLR, you say, you know what, I want to run with the stuff that's in the common language runtime. Then in that module, and in that module alone, you get trim. And you get all of the other .NET methods that are available on strings.
And also all strings that pass in.
Any string that, it doesn't change the string objects, it changes the attribute lookup behavior for that module to say, don't look for just Python attributes, look for Python and .NET attributes on pure Python objects. So it's a very nice signal that gives them a very low overhead. Trying to teach .NET developers as step one in your program is have this from under future, import this. There was tremendous amount of pushback against that. This seemed like a good compromise that still means Python code that doesn't want to use .NET features doesn't ever see them, doesn't ever have it put on them. Pure Python code remains pure Python. Once you ask for the CLR module, you can only run on IronPython. It's a module that seems unlikely to run on other implementations. So it seemed like a good tag to use for implementing this. But it was a trade-off. It was trying to please both sides as well as we could. It has methods for adding references to .NET assemblies. And it has some interop methods to make it easy to go back and forth Python collections and .NET arrays. So it's a collection, basically, of helper functions that people who are running on top of .NET need, but that I can't imagine anybody else needing. Yes?
So this might be a really dumb question, but if you get a bound method in a module that's not CLR enabled, that bound method has a .trim call in it?
So the bound method, it's the lexical scope of where the method's defined. So if the method's defined in a module that has the import CLR, that method will always work right. If you get a bound method from somebody else, where that bound method was defined in a scope that doesn't have import CLR, it won't see the trim method even if you bring it into your code, which is what you want. Because you want it from the person who was writing the code, you want what they were looking for out of the world. So, I don't know, I think this was the closest that we could come to pleasing everybody. It doesn't alter any existing Python code or any pure Python code. It lets developers easily break up their code if they want to program in IronPython to, this part's all pure Python, let's keep it all pure Python, and they won't accidentally have these .NET methods stuck in on them. And the part of code that they want to use the .NET library is the only part that's impacted by this. Yes?
Conflicts between methods that were defined in both Python and CLR?
So it turns out we don't, and the reason is purely naming conventions. In .NET, all methods, naming convention is they always start with an uppercase letter, and in Python they always start with a lowercase letter. We have a number of cases where, I can't remember the exact methods, but where we have exactly the same method in .NET and Python with two different naming conventions, with two different casings, right? Ends with is a good one. .NET has ends with capital and CPython has it lowercase. So the CLR module ships with IronPython. So it runs on top of any CLS specification. So it runs on top of Mono. That's why we call it CLR instead of .NET. We actually, naming's fun. We wanted to call it CLS, but that conflicted with things that were out there in the world. We also wanted to call it CLI. We picked CLR because, oh, I'm being taped. Because we used some search engine, and we found out that there were virtually no references to CLR. Almost every reference to Python plus CLR pointed to IronPython in the world, whereas other names had conflicting references. I used live search, by the way. Yes, that was... Exceptions.
That was delayed.
Exceptions are you get what you ask for. This one was the same thing of trying to please two different camps. I think this one, I actually came up with an answer that I'm even happier with. We'll see how you guys like it. I've got a couple more slides. Do you mind if I go? Okay. 1 divided by 0 in Python throws a 0 division error. .NET has this method called divrem in its math that divides and returns the remainder of two objects. So here's how it works. If you call it with 0, the .NET method's defined to return not 0 division error, but divide by 0 exception. Just to be fun, which happens to be a slightly different object with a slightly different class hierarchy. What we did, but you'll notice here, to the Python programmer, it looks like it's returning 0 division error. The way that we make that work is you get what you ask for when you catch an exception. And if you don't catch it, you get the default Python interpretation of it. So here, if you write try, catch, try, except, system.divide by 0 exception, which is the .NET version, you'll catch that exception. The object that you catch will be an instance, it'll be a new style instance of this CLR built-in type of divide by 0 exception, because that's what was really thrown. You can also write 1 divided by 0 in here, and it does the same thing. So we've defined a mapping between Python exceptions and .NET exceptions, where if you ask for a .NET exception and the Python exception's a subtype or convertible into it, you get the .NET one and vice versa. You also can catch a supertype. You can catch system.exception, the .NET exception supertype, and you'll get the divide by 0 one. But of course, if you catch 0 division error, you get the 0 division error, which is what you were expecting. So again, we're letting people work in whichever world they want. If they import the .NET exception hierarchy into their program, I think it's fine to let them catch divide by 0 exception with a different name. And this also let us use old-style classes for all of our exceptions, which weren't working very well until we did this, for maximum compatibility, which I've now learned was a whole lot of wasted effort, watching Guido's keynote this morning. So I'm glad that we put in that work to support old-style classes so that exceptions map on, and the warning module works right. For any of you who know, the warning module doesn't work right if you don't do this correctly. So we'll see what we get to do in the next version of IronPython when we map on to the next. But this you get what you ask for. With exceptions, it works really well because people have to very explicitly ask for what they want. So it makes it, I think, easy to provide both the Python programmer and the .NET programmer's view of the world. Because people are saying, I want this view by the type that they're asking to catch in the exception. Okay, so here's my last slide. Compatibility with CPython is going great. We're running more than 30 regression test suites unmodified and another large set modified. Code generation loves having a jet. It makes simple opcodes tremendously faster. Object layout is surprisingly identical between CPython and IronPython. That's, there's really there are not that many right choices for object layout for a dynamically typed world. New style classes turned out to be a great model. It was wonderful how well descriptors mapped onto the CLR and what we were trying to do there. And you can please all the people at least some of the time. So that's it. Here, a set of comments.